Okay, a very good afternoon, morning, evening, and night to all of you. This time around, we're going to. I'm going to discuss with all of you chapter 11 called multicollinearity. So basically, this chapter will be the idea behind the chapter will be on multicollinearity, certainly. And this particular chapter will be focusing surely again on multicollinearity. Right, let us start of this chapter called multicollinearity. So the word come from multi and collinearity. So there's two words there. Again, like the previous two chapters, these are the practical questions that you need to answer based on the issue that at hand, which is multicollinearity. So what is the nature of multicollinearity? We'll cover that part. I'll cover that part, certainly. Is multicollinearity really a problem, right? What are the practical consequences? How to detect and what's the remedial measure? This, like the previous two chapters, we have the four basic questions. Here, we added up another question, which is multicollinearity really a problem to the regression function, to the regression results that estimated by any regression. So this is part of the assumption of the classical linear regression. If you still remember, this is in chapter number 4. This should be in assumption number 10. Right, so basically that's what happened. Let us go into the first. Let us dive into what is the nature of multicollinearity. So basically, multicollinearity actually refers to what the relationship between the explanatory variables. Right, so the assumption stated that no exact collinearity between the independent variables. So this problem or this issue only exists if you have more than one independent variables. I repeat, you have more than one independent variable. If your model is y equals to alpha plus beta x, right? Like this one, a simple regression plus the mu, then there will be no such thing as multicollinearity problem. Multicollinearity problem exists when you have more than one x. Right, x1, for example, you have x2, you have x3. That should be explaining y. That's the whole idea here. Right, but the problem is that rather than the x explaining the y, the x explain themselves. X1 explain x2, x2 explain x3, x3 explain x1, and so on. So that is the idea or the issue behind multicollinearity. So this violates the assumption of the classical linear regression. So there are two types of multicollinearity. One, we call it as perfect multicollinearity. The other one is near and imperfect. All right. If it's perfect, we can determine the variable exactly from the other variable. Means that x1 and x2 are actually the same. For example, right? So let us give you this example. If perfect multicollinearity occurs or exists, then you can easily say it's like this. This is just like an equation. So x equals x1 equal to x2, right? Or here x1 equal to 2x2 or something like that. You can solve the equation easily, like a simple mathematical equation in that sense. So that is perfect multicollinearity. All right, that's perfect multicollinearity. So there are two types of multicollinearity. The other one is that if the relationship is inexact, then we call it imperfect multicollinearity. When you have imperfect, is for example, you added up this function here, because this u or this mu is called stochastic error, where is stochastic and not predictable. You do not know the value. So basically, that's what happened. Yes, you still can solve this equation, but you have to know the value of the error term. All right, so there's an error term inside that exists talking about it. But here you see the equation straight away equal to 0, but here you have another terms, the error term. So it's not an exact relationship. All right, so it's like saying that we are in relationship, but I do not know, I'm not sure, right? I'm not sure. It's like in relationship, but not really sure. So it's inexact. It's not the perfect multicollinearity. Perfect multicollinearity, you can replace one variable and the other variable, right? Okay, so that's the issue here of perfect and imperfect or inexact multicollinearity. So let us move forward into, let's say you have the problem of perfect multicollinearity. What will happen to the regression? Let's say you estimate this regression. Due to the problem of perfect multicollinearity, you'll not be able to determine the beta 1, beta 2, the standard error, and not be able to determine, because you cannot distinguish the impact of x1 and x2, and x1 and x2, for example, here are the same, right? Are the same. Okay, so that's the problem that exists here. All right, so why? Because indeterminate, because you cannot distinguish the variable. They cannot distinguish the variable cannot be distinguished. All right, so the problem exists is that you not even be able to differentiate or disentangling which one is which one. Means that if multicollinearity is perfect, the regression coefficient of x variables are indeterminate and the standard error are infinite, means that you can't estimate the regression, right? So this problem normally will not happen. Perfect multicollinearity normally not happen, but this one in reality could happen. Imperfect multicollinearity means that the relationship between the explanatory variable are strong rather than the x, right? The x variable supposed to explain y, but the problem is that the x explaining the x themselves, right? That's the idea here. For example, you have strong relationship like 0.9, 0.9 here, right? Perfect multicollinearity has been mentioned, rarely happen in a model. However, almost perfect or high multicollinearity exists in a lot of regression function in economics and finance and all the other disciplines that use such a methodology. Multicollinearity always become an issue in regression function, right? This can happen both in cross-section and time series, both, not just one. Like hetero is in cross-section mostly, and autocorrelation mostly in time series. But this one could happen in both. All right. So, for example, you can suspect there's a high multicollinearity if you use these two variables together, income and wealth. Right? It might be different measurement, but they have high collinearity because some part of it are the same. The CPI and the IPI are the same. One is consumer, one is industrial production index. Nominal and real exchange rate are actually quite similar in terms of the formula. The difference is that the nominal and the real exchange rate are calculated from the nominal exchange rate. Same thing goes to M1, M2, M3. Certain portion of the M1, M2, and M3 are the same, and GNP and GDP, we do not really put this same variable together as the explanatory variable, except you have a very, very strong reason to do that. That's the idea behind imperfect multicollinearity. So what will happen if we have the problem of multicollinearity, the imperfect multicollinearity? Regression coefficient are still determinate, means that you still can determine the regression, not like the perfect case. Perfect case, you can't even estimate. But the consequences are standard error are large, making estimation difficult. Standard error large means that they're no longer efficient, affected the variance, right? Affected the variance, affected the F statistic, and might not be blue, right? Might not be blue in that sense. But here it's stated that nonetheless, imperfect multicollinearity does not spoil the blue properties of the OLS, right? It still be, still can estimate it, but possesses large standard error, which means that the coefficient can be estimated, but with less accuracy. That's the consequences of having multicollinearity. All right, this is the issue here. So again, as been mentioned here, repeated here in these slides, and the next few slides here, is that what's the practical consequences of multicollinearity? So we have moved forward into, if we go through the question again, is multicollinearity really a problem? We have covered this one, we have covered this one. We're going to cover number 3 and number 4 and number 5 very soon, right, in this particular video. So practical consequences of multicollinearity is that when you have a perfect multicollinearity, certainly you could not estimate the regression. So no result will be out, right? Very straightforward. Imperfect is still blue. Large standard error, large variance means that it's no longer minimum, and it will affect the OLS estimator. High R square, these are the so-called the red sign, or the sign of imperfect multicollinearity. High R square but few significant T ratio. This is because of the large standard error. All right, that's the issue of one issue behind imperfect multicollinearity. All right, you can have a wrong sign. Difficult to access the individual contribution of the independent variable to R squared. Right. For example, assume that x1 and x2 are highly correlated. So if we regress, we get this result R squared. You can say that cannot precisely tell which part actually variation due to x1 and which part variation due to x2 because of the high correlation. Although the R squared is high, as I mentioned earlier in this particular subject, we want to have high R squared. But here, having high R squared and having other issues on the other side, actually meaning you're having a problem of multicollinearity. We'll see that in the next slides. Right? How to detect? So we do not really have a formal methods like hetero and autocorrelation. You have the Durbin-Watson, Bush-Godfrey, Bush-Pagan-Godfrey, White-Test, and so on, the Arch, and so on. Durbin-Hage. No, we do not have that because multicollinearity is essentially a sample phenomenon arising out from the largely non-experimental data collection in most social science. We do not have a unique method to detect, but rather we follow some rule of thumb. Right? There is no formal test for multicollinearity, but we follow some rule of thumb. So what we can follow is that you look at the regression results. In fact, this is contradict result. High R square is high, let's say 0.9, but few only significant T ratio. Means that T ratio are not significant because standard error is high. Right? So one very clear one is that high R square, right? Insignificant T ratio, and some even have wrong sign. Means that the sign is wrong. It's supposed to be positive, you get negative. Supposed to be negative, you get positive. This second part, high pairwise covariance or correlation among the regressor. Right? This can be, we can do this in eViews. VIF, we can do that also in eViews. Right? High VIF is covariance inflation ratio. High VIF, for example, the higher the VIF, the more severe the multicollinearity problem. means that the VIF normally, some literature says that it's not supposed to be higher than 5 if you solve this equation, 1 divided by 1 minus r squared. Get the value higher than 5 is considered a high a problem of multicollinearity. Right? Yeah. Okay. High r squared implies that independent variable x1 is correlated with independent variable x2 and x3. So high VIF implies, or this one here is from here, the VIF here, right? The calculation of VIF, right? The calculation of VIF, right? So high, the value mostly, some literature says 5, right? Some would say 2, right? It's available. This method is also available in eViews, but I do not really use this as a guide, but it can be as a rule of thumb. All right. So moving into next one is that let us recap a little bit back. When the r square is high, insignificant t ratio, t test, not significant. Sorry for the handwriting. T significant, not t test is not significant. Wrong sign. Those are the indication of the multicollinearity. So the issue is that, is multicollinearity a bad issue, a big problem? But the question is that it's not necessarily bad if the purpose of the model is to predict or to forecast. If you want to do prediction, high r squared is very good for the model. In forecasting, we choose the model that is overall able to predict, which is based on r squared, not based on individual. Right? It depends on the purpose of your objective of your study. But if the purpose of the model is to obtain reliable estimation of the individual parameters, then this is bad, because you want to know whether this variable x1 costs y, whether x2 costs y, and all of them actually not significant, which actually wrong in that sense, perhaps. And multicollinearity is a big issue in the regression, and you get the wrong sign, as I mentioned just now, like this. Wrong sign, high r square, few significant t ratio, but the f test is significant. And if you calculate the VIF is large, and the pairwise correlation between the x1, x2, x3 variable, the independent variable, are high, then you can conclude that that is the problem of multicollinearity, right? Then that is bad. So, how to solve? How to solve the problem? And let's say we have the issue here. How to solve it? What can be done if multicollinearity is serious? Because there's no clear-cut detection method, right? Because it's considered as a sample problem, then the solution also very much as a rule of thumb. It's not, again, like what we did in the past 2 chapters, autocorrelation and hetero. We have a very clear-cut detection and very clear-cut solving method. But here, no. You can try this following rule of thumb, the success depending on the severity of the collinearity problem. One method, extend the sample size. Extend means that increase your sample. The second one, utilizing information from the literature. We may know from previous study, for example, that B2 or beta 2, beta 3 is certain value. The literature says that the beta 2 a certain value. This one can be applied into, for example, like if you do a research on MPC, marginal propensity to consume, for example, in economics, let's say you know that the marginal propensity to consume for a country is to certain value. So if you found that your value is far away, and you want on average that you know that this is supposed to be the value, then you can say that I can use this information be a good guide for my modeling, for your model. Right? That's one example. So this is number 2 solution. Number 3, very much related to the previous chapters, transforming the functional form. Again, as I already mentioned to you, this is in chapter number 7. Double log linear, reciprocal, linear log. Transform the functional relationship. Number 4 here is interesting. Number 4 is a very interesting solution. You drop one of the highly collinear variable. Means that, let's say you have x1 and x2 are correlated. If you found out they two are correlated, so you can drop either one of these or you drop one of these and see what happens. However, it says that this may lead to another issue called specification bias. This is called this is where we can test using Ramsey reset. The best part is that following the theory, if the theory says drop the variable, if the theory says do not include this variable, should not drop the variable or should include, for example. Right. The other part of solution is that we marry cross section and time series into panel. So panel is the solution for, is one solution for multicollinearity problem. Right. The other part is that the other some rule of thumb that transform the multicollinear variables. Transform again, transformation. Right. You can transform it in that sense. You can use the first difference. You can combine the collinear variables. For example, you combine them like this. Right. Here is a 2 separate variables. You combine, you plus it, or you difference it. This is one method. This method generally is called transforming. Means that you transform the variable, you get a new variable, and you re-estimate the regression. All right. This one is already been mentioned previously in the previous slides. Right. In all cases above, solving a problem may bring to another problem. As a result, sometimes you might just do nothing. Not to say that multicollinearity is not a big issue, but it's still an issue. If you have that particular issue in the regression, you need to find the best solution and need to explain you have a multicollinearity problem because these variables are closely related to the other variable and so on and so on. And now it depends on your objective and what you want to do. So in the end of the day, sometimes you might just do nothing because doing something sometimes creates another issue that you need to solve. Right? That is for multicollinearity. So right now, right now, I think I will just stop my video here. When we do this in the live class, I will show to you how we can easily do, or actually I've shown it to you, we can easily do the correlation coefficient analysis that you have done before this, but I'll show you another time to do this multicollinearity issue here. This one, right? I will show it to you in the when you do the class on this particular chapter. We talk about this correlation in eViews. You can easily do in eViews. All right. Okay. So for time being, that's what I have for time being in this particular video for today. Thank you very much for listening to me. I wish all of you and pray all of you stay safe, stay healthy. Bye-bye, adios, and stay safe. Bye.